Okay. Okay, now that I tested that everything is working, I apologize. This is a repeat of a class we did, and unfortunately I forgot to record it, so I have to do it again. So it'll probably be a little different. Certainly doesn't have any questions in it. And hopefully most of it will make sense. Usually things that don't make sense get caught by other people, but right now we're going to be stuck with just me. So we're dealing with decoherence and quantum mechanical evolution to classical. And this is part 3. We're going to deal with the abstract, which we've dealt with several times. Introduction of what we're dealing with today, review of entanglement. Then we're going to do new material, which is isolated, closed, and open systems. And then we're going to start on coherence and decoherence. And we're not going to finish this. Next week, there is another lecture. Okay. So several lectures ago, we started discussing spaces, especially configuration space. Configuration space is important because as Schrödinger, I think 1926 or something like that, pointed out that the wave function does not operate in space, it operates in configuration space. And this is the reason for non-locality or locality. And although information in space can't travel faster than the speed of light, the collection of particles in a wave function are at a single point in configuration space. And in fact, they behave as if they were a single system. This is the essence of entanglement. Entanglement was another word that was defined or used or developed by Schrödinger, but he didn't originally understand it, or, well, he understood it to some degree, but in response to Einstein, Podolsky, and Rosen's paper in 1933, I believe, or 35, he coined the word entanglement first in German and then in English. So, as you may or may not know, the Schrödinger equation is linear. This means that there are a collection, if there are a collection of n solutions of the Schrödinger equation, we call the collection of them psi sub I goes from 1 to n, then any linear combination of these solutions is also a solution. And this is a general result of quantum mechanics, but it's critical to entanglement. So if there are n solutions, we say the position of a single particle where the wave function exists in configuration space. Configuration space is 3n space degree. And people typically say that the particle is here, x, or there, x prime, or another x double prime, or yet another x triple prime, and so on. But it's actually at all of those places simultaneously in configuration space. So, what is a measurement? Not necessarily a human observer. It's not a mouse or even a virus. It is rather any interaction between any two quantum theory systems. When they interact, they become entangled. And that's the definition of a measurement, the entanglement of a quantum system. So, what's an isolated system, a closed system, an open system? We're going to talk about this a lot today. An isolated system, these are thermodynamic ideas, and they all assume that you're in equilibrium. But an isolated system is a system that cannot exchange energy or mass with its environment. To prevent work from being exchanged, the system must be rigid, that is, it must be constant volume. Prevent heat from being exchanged, the walls have to be perfect insulators. Obviously, it's the Duncan experiment, not a real one. Closed system is one in which matter, mass, can't enter or leave, but energy can be transferred from the surroundings in two forms, work and heat. This is typically what a laboratory system is actually like, and in these cases, most people simply correct theoretically or computationally for the exchange of energy that goes on between the two systems. Finally, an open system allows the reacting system to exchange matter and energy with its surroundings. And reality means, and that's what almost all systems eventually will be like. Reality, that's the place we're trying to get to. And reality means systems are composed of beables in the sense of John Bell. It means that if we do repeating a measurement, we should get the same result. And different observers measure the same result. We don't restrict the meaning of an observer to be a human being. Decoherence, this is what we're studying, and it explains or describes how quantum theory becomes reality or classical physics. And the ideas were used for many different ideas, but one of them is only fit, borrowed from Darwin, or robust states of measured quantum systems shall survive the measurement interaction with an environment. And this is a process called Ein selection. The environment has many copies of the system state recorded, and these become the basis of the wave function and are called pointer states. So, although there can be many bases, the robust ones are the ones that we call pointer states. And therefore, observations can be made without destroying all the records stored in the environment. You can use one of them to do a measurement, but there'll be many stored in the environment. And that's what enables observers to agree on the features of the system. And that's the measurement non-problem. So it should be noted that if a measurement is carried in a laboratory and the human experiment chooses to measure property A, while another chooses to measure property B, and if A and B are not compatible, which means the operators for those two measurements do not commute, then the two experimenters will not agree on a common reality. And this is what we call reality, where everybody measures the same result. Okay, introduction for today. We described the correspondence principle, spaces, especially configuration space, and we did a pass of a form of entanglement. This week, we're going to focus on closed systems, open systems, decoherence, and the quantum theory of open systems, which brings us to decoherence and the classical world. We'll finish up with, eventually, not this week, some experimental results showing this behavior. And we'll note that the concepts of an isolated system, a closed system, are thermodynamic ideas in equilibrium, and they're never actually physically realized. They're idealizations. So if you take a look at the picture moving from right to left, each type of system, going from an open system to a closed system to an isolated system, gets more and more constrained and restricted in terms of exchange of matter or exchange of energy. As I think said, in the universe, only open systems are exhibited. And this is important in understanding the evolution of entanglement and decoherence. As an example, think of the most complex quantum computer created today. Decoherence times for candidate systems typically range from nanoseconds to seconds when they're put at very, very low temperatures. That is almost no energy going in. So currently, most quantum computers require their qubits to be cooled to 20 millikelvins, 20 thousandths of a Kelvin degree or less, in order to prevent significant decoherence. And about the longest that 15 qubits, I believe, have been able to exist is about 200 seconds. So after that, the environment interacts with the system and you just lose everything and it becomes decoherent. So let's do a quick review of entanglement. Quantum entanglement is the quantum law, is a function of the quantum law of conservation of information. Quantum law of conservation of information states that information cannot be destroyed and is satisfied at all instants in the universe. So the information is distributed throughout the system and the environment via entanglement, and it's based on the wave function of the universe. So a quantum interaction is the same thing as a quantum measurement. A laboratory experiment is the result of many interactions. Unfortunately, because of contextuality, which we looked at previously, any measurement or interaction is a result of a particular sequence of interactions with its surroundings. The rules of quantum interaction follow the rules of the contextuality game that we did last time. In that game, we had 6 physicists, mathematicians, and engineers. Each person answering can be considered to be an interaction between quantum systems. So the information gained through each interaction becomes part of the system, and the system is not just the interaction, but also the observer and the interaction. If you remember the game, the way that we did it, nobody had prior an answer for what the physicist or mathematician or engineer was. Somebody would go out of the room, everybody would know that the rules were they had to answer with their particular answer, whoever they were thinking. And then after that first answer was chosen, everybody else had to conform to that answer. So if, for instance, it was an ask of whether the person was female or male, whoever answered with their particular person in mind, if they said it was female, then everybody who had a male choice had to change their response so that they had a female person. And then you do the next question. You could ask if it was a mathematician, and if it was a mathematician, all the physicists people who had chosen physicists or chemists or engineers would all have to change to a choice of a physicist. And that's whatever I just said. Anyway, eventually everybody gets to the point at which all of the questions that have been asked force everybody to have a single result. And that's the process that goes on in quantum theory to give a measurement. You have a sequence of yes-no questions, and eventually those give you a particular result, and that's the measurement. So if you were looking at this, what would happen? You'd be putting together, say, a jigsaw puzzle. Somehow the box got lost, so you don't know what the picture is supposed to be. You put the puzzle together starting from the outer edges, and you find a picture of a cat. Oh, very interesting. Then you break up the puzzle, put it together, but now you start from the inner pieces. And it's the same pieces to the same puzzle, but this time, when you put it together, it's a llama. And if you think this is weird, it's just the contextuality game. And that's the way quantum mechanics works. So the result of a lab observation represents on a sequence of interactions of computer systems with all the parts of the environment, and it has interacted with its interactions from all of the other atoms in the laboratory measurement system and photons that have been going through, etc. So, as an example, two particles are entangled because they're bound by a relationship of information. And as an example, we'll consider two particles that are entangled so that their net magnetic moment is zero. If both the particles don't interact with its environment, and the magnetic moment of the particles, that is, if the laboratory has a Faraday cage so that there's no photons that can enter, it's at a low temperature, millikelvins, etc. So the particles will not entangle with the material unless they actually go into the Faraday cage, or every once in a while there will be a photon that comes in no matter what. Anyway, as long as they don't interact with much of the system, the magnetic moment is zero, and the value of each magnetic moment will essentially be random. However, once one of their parts of the system interacts with enough of a laboratory that you actually can understand what the net magnetic moment is on one of the particles, then the other one, because they're zero, we know the rest of it immediately. And this is just a function of the fact that the information is always the same, and we satisfy that information relationship that was bound initially, and the law of the conservation of information means that that relationship must be always true. And as I said, once you know one of the particles, you know the other one. So this is why a second polarization of two entangled photons can be known by discovering the other photon's polarization. The classical analog for maximally entangled photons is Bertelsmann's socks. The article that was written by John Bell. So, isolated, closed, and open systems. A thermodynamic system is a body of matter or radiation confined in space by walls, which have various defined permeabilities, that is, some amount of energy or matter can exchange between the surroundings and the system. Two thermodynamic systems may be contiguous or immediately adjoining one another, and certainly the surroundings are usually a thermodynamic system. And in many cases, for open systems at least, the wall between them is purely notional. That is, we arbitrarily select what's inside the system and outside the system. When this is true, we call them to be permeable to all matter, all radiation, all forces. However, we have a couple of special kinds of systems we called isolated systems, systems in which the body of energy and matter is completely separated from its environment. So an isolated system means that no mass can go across the boundary and no energy can go past the boundary. And no mass from outside the system can go in, and no energy from outside can go in. So an isolated system requires walls to be completely non-permeable, that is, separated from the surroundings so that no radiation, no mass, or any energy can pass in either direction. A closed system is not as completely non-permeable as an isolated system. A closed system keeps mass separated from the environment, but radiation and energy can pass in the boundaries, and these are called closed systems because they're partially permeable. An open dynamic system allows mass and energy to pass between the systems and the environment. So this is the case of where the boundary is purely notional. We arbitrarily choose where it sits, but the environment, all of the energy and mass completely goes through or between the supposed boundary. As I've said several times, isolated and closed systems are idealizations, limits that you never actually attain, at least not for long periods of time. So for all quantum systems, they will spread the entanglement, essentially, all of the universe. In terms of photons, just as an example, there's quite a few of them in the cosmic microwave background, about 400 per cubic centimeter, always. So think about a sphere of radius 0.62 centimeters. This gives you a sphere of 1 centimeter cubed. So the electromagnetic field, we know, travels across the diameter of the sphere in about 4 times 10 to the minus 11th seconds. So on average, about 400 are in the sphere. Total number of photons per second is about 10 to the 13th photons. And if you're in a place on the Earth, the atoms will be in the atoms in the gas will be in the room, atoms of the experimental equipment, etc. So entanglement of a quantum system spreads about incredibly fast over an incredibly large number of interactions in space. This is just a picture showing 400 light rays passing through a sphere, some going in, some going out, through a sphere of volume 1 centimeter cubed. So to summarize again, isolated and closed systems are idealizations. All systems are eventually open systems and deal with the environment. Decoherence is based on the fact that quantum basis of local environment evolves. and the most prevalent basis becomes in each region around a quantum system. This prevalence is called line selection, and although in any quantum system there exists a diagonal probability basis, this process occurs naturally in decoherence and becomes robustly present. And and they're called pointer states, and for this reason, we call it the non-measurement problem. Okay, let's deal a little bit about coherence and decoherence. Coherence deals with the degree of correlation of propagating electromagnetic waves. Lasers, for example, emit light that's strongly correlated and highly coherent. The sun or incandescent light bulbs emit weakly correlated waves. Thus, this light is generally said to be incoherent. To be a little bit more precise, they're characterized by a low yet measurable degree of coherence or correlation. So what is quantum theory correlation? The word decoherence is a physicist's invention. We would, if it hadn't already been chosen, classification, meaning to become classical. But classification was already meant with another meaning, so they chose coherence and decoherence. To decohere means to become less and less coherent, to lose coherence. And in the quantum physics context, the word coherence typically means the quantum features of interference and superposition. Superposition being the sum of linear solutions. Interference is due to the fact that the coefficients in the wave function are complex numbers. And because of that, all of the features of the quantum system behaves non-classical. So during the process of decoherence, these features get lost. The system becomes behaving in a more and more classical way. From a naive observer's perspective, more classical behavior could be called more coherent in the sense of more intelligible, but not in the quantum system. We call it decoherence rather than coherent. And we see that in decoherence, the process classifies, that is, makes the system more and more classical. This is the other way of calling it classification. A quote from Richard Feynman. A philosopher once said, "It's necessary for the very existence of science that the same conditions always produce the same results." Well, they don't. And we'll take a look at a little bit about coherence and decoherence in the two-slit experiment. So on the left, we have a set of coherent waves in a two-slit experiment. Now, the coherent waves, what are coherent waves? It means that all of the waves that are in the material that's waving, be it a field or water or whatever, have the same wavelength. So you can take the power spectrum or periodigram of the image on the left. And basically, all of these waves are spherical wave fronts. So our power is circularly symmetric. There are a few parts here where you see there's a little bit of strangeness going on here and some coming on here. And as Bob Witkowski pointed out in the lecture, this is due to the fact that the picture we're using as for the power has boundaries, and therefore there's some edges from here and others from here and here and here, which are causing these slight interactions between them. But basically, the system is circularly symmetrical because the waves are spherically symmetrical. And they're essentially all right here in a particular frequency. Now, again, this is an image, not a power spectrum or a Fourier transform of the actual values of the waves, but the image, and so it's smeared out slightly, and it's around here. Okay, so the idea of coherence is that all of the waves are exactly at a particular frequency, and they're symmetrically, circularly symmetrically positioned. So what if we add 6 pairs of random wavelengths, each one on a different slit? So here's 12 sets of frequencies. There's one here and one here on each of the slits, a different one here and here, 2 more, etc. So for every point on the slit, there's a 6 different wavelengths, random wavelengths. Now we add those coherent waves to the original coherent wave and do the power spectrum again. So we notice that it still has considerable amount of power in the original wavelength. Whoops, sorry. But when you take a look at it, you see there's some more frequency out here, frequency here, frequency here. The purplish regions, not these regions, are due to the various frequencies that are being added together. So we get it even more decoherent. We have 30 random wavelengths on each slit as an approximation for non-coherent. A truly non-coherent system would have an infinite number of wavelengths. So this still has a fair amount of power around the original, but now we can see there's some out here and some more here and in here and in here and etc. So all of those images in the power spectrum show that you have spread out the energy. And in a totally decoherent system, you would have an infinite number of wavelengths, and all of the energy would be everywhere. So let's talk about 4 physics who were important in understanding decoherence. Eugene Wigner, who's up here, John Wheeler, who's here, Dieter Zeh, who's here, and Wojciech Zurek. So all of the names here are left to right, top to bottom. Eugene Wigner developed in 1932 what he called a quasi-probability distribution to study quantum corrections to classical statistical mechanics. The goal was to link the wave function that appears in Schrodinger's equation to a probability distribution in phase space. And this is the Wigner function for a Schrodinger cat state. Now, in 1949, Jose Moyal derived it independently and recognized that it was a quantum moment generating functional, and thus a basis for an elegant encoding of all of the quantum expectation values in phase space. So a moment generating function, you can take a look at a distribution in terms of either its probability distribution function, or equivalently, you can look at all of the information in terms of its moments. So you can take the mean, you can take the variance, you can keep taking the skewness and kurtosis, and each power of the value of the distribution has a name, and you keep doing the expectation of those powers, x squared, x cubed, etc. And you can get an equivalent infinite list of numbers that describe the probability distribution function. And there is a way of calculating all of those those moments, that infinite list of moments, as coefficients of a Taylor series of a function. And a function that has that kind of a Taylor function series is called a moment generating function. So I found out that most people don't seem to know what a moment generating function is, so next week I'll talk a little bit more about it. John Wheeler contributed a tremendous amount of physics, and not only quantum mechanics, general relativity, and especially his PhD mentoring. Charles Misner, Kenneth Ford, Wojciech Zurek, Kip Thorne, Daniel Holtz, Richard Lindquist, Robert Girard, Robert Walt. There's just an ongoing list and list of people. The list here shows 17, each of which published more than 100 highly respected articles and those 17 out of 46 students that Wheeler supervised. Wojciech Zurek is the one who has developed decoherence as a way of describing quantum theory as a basis of classical physics. This was originally understood by Dieter Zeh, who was not a student of Wheeler. However, he's primarily focused, once he understood that there was a evolution of the quantum theory to classical systems, and showed a few small models of that kind of evolution. He focused rather on decoherence, or I shouldn't say on decoherence, on the evolution of decoherence to the classical, but rather the irreversibility in decoherence and its relevance to the arrow of time. And he died in 2018. We're not going to talk about that. We're going to talk about what we've been describing, coherence and decoherence, and its evolution to the classical. It's another whole interesting, very way of looking at how time and its direction of flow occurs due to decoherence. So we've talked about how decoherence compares classical physics to quantum mechanics via the measurement in both. An example is given by the LIGO gravitational wave detector, which uses the indeterminate force on a mirror from the momentum transfer of photons. And this is one of the largest quantum physical systems ever developed. Each mirror is 40 kilograms. And yet the limits on the ability to measure the interaction of the gravitons with the system is the limit is due to the quantum effects. So in quantum mechanics, one usually only need to amplify any quantum effects because they occur on such tiny scales. And this was what Niels Bohr called crossing the borderline. In his mind, we talked about it before, about the correspondence, that in point of fact, there were two realms of physics. One was the quantum theory and the other was classical. And he never was able to describe how this border between the macroscopic and microscopic was defined. And Bell called this the shifty split, because every time you talked about it, he would talk about something different. The precision that we need defines part of this line, and also the simplifications that we make. So, as I've said before, decoherence is loss of the ability to interfere. It happens because the exchange of information and energy between a system and its environment gets entangled. Jurek considers quantum chaotic systems, and we have talked with Bob Lukowski in a previous set of presentations about chaotic systems, but I'll repeat what he said. A chaotic system is characterized by its strong dependence on initial conditions and on perturbations. This is the butterfly in Peking gives a tornado in Ohio idea. But for this example, we'll use the Baker's map, which I'm using because it happens to be isomorphic to various ideas in quantum spin glasses. And essentially, when you take the Baker's map and the area gets stretched and pressed and then folded back together, and this leads, after a few iterations, to a complete disruption of the initial structure. So what's the Baker's map? If you take a look at a region of 0, 1, 0, 1, that's an area x from 0 to 1 and y from 0 to 1, then if xn is between 0 and a half, you just double x, and y is some scaling factor times y. If it's in the rest of the x region from 0.5 to 1, then you double it still, but you subtract 1, because, of course, in the region between a half and 1, it's going to be greater than or equal to 1, so you got to move it back down between 0 and 1. And the y is scaled by the same amount, but you add 0.5. Now, a is a parameter, and you choose it for the map, and it's fixed for every iteration, and it's a value between 0 and a half. I'll show a few simple pictures showing the iterations of a Baker's map. We start with an image on the left, and as I said, you stretch it, so you actually stretch it so that it's twice the length, and then you fold it so that the left portion goes to the top. And that's one iteration of the Baker's map. It exists sensitive dependent on the initial conditions. That is, it depends on the stretching in the x direction. And as you do it over and overly, it eventually becomes a Cantor-like set. So here's 5 iterations. You start with the original value, the 0th iteration. Then you have the first one that, as we said, it was stretched to double the length, and then you take the left portion, put it on top. Then you do the same thing for that one to get the next one. So it gets stretched again and folded again. And then here you can see there's 1, 2, 3, 4, 5, 6 versions of this in it, and it keeps getting more and more stretched, and eventually, if you do enough iterations, you just get lines. So for a quantum system, this means that the initial distribution in phase space gets folded and stretched. And after a certain time, it exhibits fine structures, all of these lines. The Wigner function changes its sign. This leads to interference. And Zurich argues that friction destroys the quantum structures. What do we mean? That it means that the system no longer shows interference and approaches a classical system. So how can we look to friction? And the way we do that is by diffusion, the usual heat diffusion process. And we use the differential equations for Brownian motion. And this has the same structure as heat diffusion, but we apply it not to gases or liquids, but to the Wigner function that we've talked about previously. And a typical solution for the Wigner function of a system under the influence of friction has a certain characteristic time scale, or 1 over the time scale gives us a rate at which decoherence occurs. So the Brownian motion, using the differential equations for it and the Einstein relation between friction and diffusion, balancing the loss of gain of energy and loss of energy yields eventually a thermodynamic equilibrium. That process is very complex, and we typically don't talk about the equations, but we'll look at this particular one, which is that characteristic time scale that we were talking about. And for the Wigner function, that time scale is h bar squared divided by 2 times gamma m k sub b t and a squared. What are all of these coefficients? Well, gamma is a friction coefficient, and it has units of seconds, and we're going to choose it to be 10 to the minus 3. The m is the mass of the quantum system, and we're going to say it's pretty large, 10 to the minus third, 1,000th of a kilogram, that is a gram. And A is going to be something of typical size here. We're going to call it about a micrometer. So a millimeter is 1,000th, so 1,000th of a millimeter. Temperature is going to be roughly what we see in a laboratory, 300 degrees Kelvin. And for such a small macroscopic object, we find a typical decoherence time of 10 to the minus 29 seconds. So this is the time during which equilibrium occurs, and this time scale is an incredibly short one, but it's typical for decoherence times. So we've talked a lot of things, and we had a lot of talks last week. We didn't get where we needed to get to, but we're going to finish here, and next week we'll do line selection, pointer states, and we're going to talk a little bit about something that is called decoherent histories or consistent histories. And this is a set of an interpretation of quantum mechanics that was developed by a whole bunch of people, Gell-Mann, Hartle, Robert Griffiths, Omni, a whole bunch of people who have developed this between the 70s and the and current, and it provides the probability and logic in entanglement and shows us why quantum mechanical is classical when you're 6 feet tall and about 10 to the 24th atoms all entangled as a quantum mechanical system. And then lastly, next week, we'll talk about experimental results. So this has been a reproduction of what we did in class. And of course, there were many questions that I don't remember what they were, and I tried to express as many as I could, but I'm sure I left some things out, and I apologize for not recording this in the first place. But for next week, have fun.